but I think the ideas that I want to propose, I think, should be related to the things they did, although the relation is still not understood. So, I mean, the basic idea is to try to get the proof so it's small radius by using the perturbative super Yang-Mills, which we understand very well, and the string theory on small radius, which we don't understand very well. And the basic idea is to do something like what Tufte's idea, which is that essentially if you have, so if you think of computing some scattering amplitude, or some, I guess, correlation function. So if you have some trace of some state here and some other state here, and let's suppose we just want to do this at tree level. So if these are the three vertex operators for these three states of V1, V2, V3, then we can imagine that this can be understood as some state made up of singletons. So this would have n singletons. So each phi would be like a representation of super Yang-Mills. This would have m and this would have p. So let's suppose, I don't know, let's say this is 3 and 2 and 3. And then if you're just doing free super Yang-Mills, then you just have propagators connecting these. And okay, so the propagators, and you get three codes. You might have some propagators, I guess. Something like this. So this would be a one over n expansion. This would be a lowest order in 1 over n. And this would just be your free super Yang-Mills because you only have propagator. Okay, so I think this diagram is clear to everybody. And I think it is a sphere diagram just because all of the holes here are just disks. Everything is simply connected here. Then if you want to introduce interactions, so still at this is free super Yang-Mill. Because you just have propagators. Then if you want to have interactions, then you put in some vertices.
Sorry, is free super Yang-Mills at large n or any n?
Large n.
Large n.
So if I wanted to consider 1 over n corrections, then I would have to allow, for example, holes in these disks. So I would have to have higher genus surfaces. And you would have windings and things like that. But let's just stick to large n for now. Okay, now if you want to have interactions, so for example, you have two vertices here. And if it's two big vertices, then you could have this type of diagram. So this would still be a sphere because it's all planar. But now you have two vertices, so this would be at each vertex you get of course a Yang-Mills. So this would be higher order. This would no longer be free super Yang-Mills. So this would be, of course, some radius dependence coming from. And would be the Tuft. So this would be related to R to the fourth. Okay, so the question is, can we get this type of description from the string theory? So what the speculation is, or conjecture, however you want to say it, is that at 0 radius, which corresponds just to free super Yang-Mills, the action is just a topological action. So it's just going to be Q lambda. Where the idea, so Q is supposed to be, of course, the BRST operator. I'll tell you more explicitly. And of course, it's topological in the sense that naively, if all the vertex operators are BRST closed, then of course nothing should depend on, if I put a parameter here, nothing should depend on this parameter. Okay? So A, you can take whatever you want, and essentially the amplitude should be independent of small a.
Sorry, Nathan, to bother you. So there are two parameters, G-Mills and N.
Yep.
So how are we taking? Sorry?
So N is going to appear because when I do my functional integral, I can either do it on a sphere or on a homogeneous surface. So I'm doing string theory. So I have the usual lambda string 2g minus 2, but this is the genus
Right.
of the Riemann surface. So that's going to be related to, of course, N, because lambda string is G string. So if I think of r to the fourth over N, then I guess let's call it G just like this. So this is going to be related to G string, right? So if I expand the genus string, that's the same thing as expanding like 1 over N. Okay, so that'll give the usual 't Hooft expansion 1 over N. And then the other parameter is going to be a term that so this is free. So of course free, there's no other parameter. Free super Yang Mills, you only have N. You don't have G Yang Mills. So the idea is that if I look at the free super Yang Mills case, then I'm not going to have these vertices, of course. And then the idea is that the worldsheet of the string is going to somehow, what do you say? You can think of these as some kind of saddle points, but because it's topological, the saddle point approximation is exact. So somehow it's going to divide into just, instead of being an integral over all, over the moduli of the punctures on the sphere, it's just going to become a sum. So that's, of course, the same thing that happens in these ambitwistor strings in the description of Rajesh and Matthias radius becomes S3. So that's, of course, natural to think that it comes from some topological string because you get a sum instead of a function. Okay, and then this other term is going to be related to the radius. So it's going to go like r squared. And it's going to be multiplied by some other factor, which I'm going to call b. I'll tell you what this b is.
This is the worldsheet action we're writing.
This is the worldsheet action. So the idea is that this r squared, that's the first, in some sense, evidence that this is on the right track, is because r squared is, of course, related to G Yang Mills. So r squared is the square root of the 't Hooft coupling. So this is actually not G Yang, this is the square root of the 't Hooft coupling. So the fact that each vertex comes with the square root of the 't Hooft coupling means that it's related to r squared. And r squared is, of course, the coefficient in front of the ADS5 times S5 action. So this is at least one piece of evidence that you're on the right track. Okay, so now, of course, I have to tell you what Q and P is. That's going to come later, but Q is going to be related in the pure spinor form. So, of course, this idea, in some sense, the pure spinor form is, I think of this as a realization of this, but of course, there might be some other way to realize what Q is. And B is going to be some antisymmetric Q form. I don't know, you guys know more about topological strings than I do, but it seems to be important that this is an antisymmetric two form, so that it's independent of in some sense, it's independent of the two-dimensional metric. And I'll say one more thing that I've never seen anywhere, but it seems to be important. So you want to reproduce a cubic vertex, right? So this B term is supposed to reproduce the cubic vertex here. Now, I don't know anything about how this works in the ADS3 times S3, but for Super-Yang mills, of course, I know what the cubic vertex is. So it's something like, so this is now Super-Yang mills. So there's a term here, F. Plus. So it involves a commutator here, right? And the claim is, or the conjecture is that this two form, the fact that it's antisymmetric in Z and Z bar is going to be related to the fact that it involves a commutator. Because what the commutator does is, if you think of it as, so if you have some, oh, I should have said this already, this vertex you can think of blowing it up. So it should be something, if it's a cubic vertex, you should think of it as the same thing as something like a trace where the three fields are just precisely these three fields here. Right? So this would be like an F, an A, and A. But it's a commutator, so it's this thing minus. This is A1, 2, A1, minus and drop the door. And the claim is that if you try to build a two-dimensional Lagrangian which tries to reproduce this kind of vertex, it's going to be something which is antisymmetric in Z and Z bar. So that's what's going to give you this commutator. Okay, so that's essentially the introduction, and then the rest is trying to piece together different features of this.
Wait, so that last thing you said, was that supposed to be clear or?
No. So let me say it more specific. So suppose we have something this form. A on the worksheet. So we need to have three things, otherwise it's a total derivative. So this would be something which is antisymmetric. And I'm not going to tell you what A, B, and C are at the moment. Okay, so the claim is that now I look at some lattice version of this. So this is going to be something like A d dx. If I think of x and y as d dy c minus a. And now I just think of this as being, put it on a square. And I think of d dxb as just being the difference of, first I put b here, and then I put minus, and then I put b here. So that gives me this difference. Then if you look at how it works out, you're going to get something like a, b, c. Of course, if I do a cyclic permutation, it doesn't matter. But you can always end up getting two terms where you have a difference if the things are cyclically ordered A, B, C, or if the things are ordered A, C, B. So that's the way I understand how this antisymmetric form is going to be related to this commutator.
In your mind, is there a one-to-one correspondence between the fields on the worldsheet and the fields?
No. So there should be a one-to-one correspondence between the vertex operators. The vertex operators for singleton
Right.
on the worldsheet, so if you like the BRST invariant singleton operators and the fields in Super-Yang mills. But you're right. This A, B, and C, I'll say a little more how they're related to the Super-Yang mills things later, but it's not one-to-one. It's more complicated.
So the antisymmetry here and the antisymmetry there are some steps between.
So when I say the antisymmetric here, so what I mean by A, B, and C?
Yes.
So this A, B, and C are just worldsheet fields.
Right.
But I didn't tell you how this A, B, and C worldsheet fields are related to the Super-Yang mills fields.
Right. But on the Yang mill side, there was this antisymmetry in terms of Yang mills fields.
In terms of the
Yang mills.
right. So eventually, this A, B, and C are going to be related to Yang mills fields. But I didn't tell you how they work. I mean, I can sketch it, but essentially X gets related to the gluon, and theta gets related. So this is related to the gluino, and the field strength, that's a little bit strange. The field strength is going to be related to something related to these pure spinors.
So there's a simple close connection between the fields and the...
It's a simple closed conjecture. I mean, I can't say anything more than it's a conjecture.
Yes. And sorry, those diagrams there, that was meant to be a blow up of the interacting part of the Feynman diagram?
It's supposed to be this vertex here.
Yeah.
So sorry, so the statement is that, let's say that you don't know anything about string theory, so you take n equals 4 super-animals, you compute this 3-point function to 5 loops, you write things instead of in G animals and n, you write things in terms of R and G string, and then you set R to 0. And your statement is that answer can be obtained from this worksheet.
Yeah, so R to 0 just means it's just a free case. So that would be just free superhelium. And if you put in R, then you also include so that if you include R, it's really just a full perturbative superhelium expansion. You're not missing anything.
I think maybe what...
My confusion is that in G-animals we have 2 parameters, G-animals and n.
Yes.
And here I would like to see what are these 2 parameters. Like I understand that it's R and GS.
Yeah.
I see.
So you want the relation. So the relation is that
Oh, I get it. Thank you.
this is a
Yeah. So R is the correction to AQ lambda, and then we have the usual loops in a string. Thank you.
yeah.
That's perfect.
Okay. So the next thing to explain is what's this Q.
Before going on to the interactions, one could already ask what the spectrum of the free theory is.
Yep.
That you will.
So the free theory, in some sense, on this side is trivial. It's just the product of singleton representations. Getting it from the vertex operators, that's I'll say how I think that works. Okay, so we have to start with Q. So what is Q? So Q obviously has to be nilpotent. And it has to describe what the physical states are of the theory. Okay, so the intuition for Q starts by understanding superangles in 10 dimensions. So this is something that is naively unrelated to ADS 5 times S5, but of course it's related to 10-dimensional open string theory. So if you try to describe superangles in 10-dimensional superspace, then so this is D equals 10. So no string theory yet, just D equals 10 superangles. Then it's natural to introduce a pair of superfields. This superfield is the superfield whose lowest component is the usual vector. And this superfield is a superfield, whose lowest component is not the gluino, but it's actually a gauge field, and the gluino sits at higher order. So this construction, you can think of this as being the gauge field. So D alpha, maybe people are more familiar with. So in 4-dimensional superspace, this is just the usual superspace derivative. So we have dx and essentially the same thing in 10 dimensions. And dm is of course just the usual. So when I write small a or small m, it's always a vector index. And when I write small alpha or small mu, it's always speed. Okay, so alpha is 1 to 6.
So A alpha is a fermionic field.
A or n is always 0 to 9.
So is A alpha the gluino?
No, so it's not quite the gluino. So it's, I'll tell you where the gluino sits in the superfield.
Okay.
So dm is of course the usual vector derivative. And then we covariantize dm, of course you get del m is dm plus am. And when you can covariantize d alpha, you get now, of course, even if you're in flat space, the torsion for del alpha, del beta is non-zero, right? Del alpha, del beta. You know, flat space is just equal to gamma m alpha beta del m, right? Because it's just the usual superspace anti-commutator. What that means is that if you take d alpha is A beta and anti-symmetrizing alpha and beta, you get gamma M alpha beta AM. So this superfield is related to this one. Let me call it M. They're not unrelated. Okay? So if this starts with the gluon, what you find is the gluon is the theta component of here, or let's call small a the gluon. That's the gluon. And then the gluino sits at next order in theta, so you get something like theta, different ways to write it. So this is the gluino.
So the zero component of A alpha is some auxiliary field.
That's right. It's actually a gauge. And the higher components in theta can all be related to the gluon and gluino. So the gauge, I told you what the gauge fields are. So obviously the gauge transformation is delta A alpha is equal to del alpha of delta AM is equal del M over omega. So these are the gauge transformations. So using this gauge transformation, you can easily see that you can gauge away the lowest component of A alpha. Now what about the equations of motion? So it turns out in 10-dimensional super A mills, this implies the equations of motion. So once you impose that, you're essentially stuck with super Yang mills. There's no corrections to the 10-dimensional super Yang mills, because this fixes the equation of motion. Okay, so this looks like a definition of AM, but it's actually more than a definition of AM, because it implies that the phi form here.
So where's the coupling constant? Oh.
So I'm doing, if I do Maxwell, then of course there's no coupling constant. If I do super Yang mills, then the coupling constant's here. So I'm just, I can of course put the 1 over G squared in front of the action. So, but it's always, whenever you have a commutator, you have effective G. Okay, so this equation here, let's just do Maxwell just to simplify things. It implies that if you take d alpha of A beta and you symmetrize, but instead of symmetrizing with the 1 form, you symmetrize with the 5 form. So it turns out in 10 dimensions, a symmetric 2 form, symmetric bispinner, can be decomposed to a 1 form and a 5 form. And this equation here implies that the 5 form is 0. Because obviously if you take d alpha of A beta, you only get the 1 form. So you can think of this as being the equation of motion, and this as being the definition of
So all these things are if and only if, so they imply each other.
That's right. Of course, to go this way, you think of it as the definition of AM.
So is it right that the closure of the supersymmetry algebra implies the equations of motion?
Yeah, if you want, you could say it that way, yes, sure. That's of course in 10 dimensions.
So it's one shell is superspace.
So all we're going to do is all one shell. Okay, so this is just the definition, this is just the justification for what we're going to do with Q. So the idea is now the vertex operator, now we're doing string theory. This is now open string theory. The vertex operator for the super Yang-Mills multiple is going to be this object here, where lambda alpha, so this is what's called a pure spinner. I'm going to say it's a ghost because it has the opposite statistics of what you would expect for a spinner. So it's bosonic. And pure spinner means that it satisfies lambda alpha. You take the bispinner with itself, you get 0. So that's the definition of a pure spinner in 10 dimensions.
Sorry, back up question. So the fact that it's on shell means that you cannot write the action in terms of these superfields?
Right. You can write the equations of motion, but you can't write the F. Okay, so this is the definition of a pure spinner. And it implies that lambda, instead of having 16 independent components, has 11 independent components. So this is studied Cartan in arbitrary dimension. But, the reason why we're going to do this is because now we're going to define Q to be equal to lambda alpha d alpha. So what that means is that QV equals 0. So this is nilpotent. The Q squared is going to be lambda alpha lambda beta. Now you have the anti-commutator d alpha with d beta, but that's 0 because of this identity. Right, because this is equal to lambda alpha lambda beta gamma alpha beta m dxm. But we decided this is 0, so this is equal to 0. And QV equals 0 implies exactly what we want. It implies lambda alpha lambda beta d alpha a beta equals 0. Again, because this is only the 5 form part of this contributes, this implies that gamma the 1 form part here doesn't contribute to this because lambda gamma lambda equals 0. So this is the equation 1. So what we found is, and of course the gauge transformation delta V equals Q omega is just Q omega is equal to lambda alpha D alpha omega. So this implies delta A alpha. So if we produce the equations of motion and gauge symmetries of A alpha using this BST. So this was essentially first understood, not in string theory, but just in superheating mills by Paul Howe. Okay, so that's essentially with the Q we're going to do. But of course, we're going to do the Q for the closed string, not for the open string. But the idea is that for the closed string, now it's going to imply the closed superstring equation. The equations of motion for the closed superstring vertex operators. And of course, one of those vertex operators is the...
So is it true that the whole action for n equals 1 superheating mills intendi can be written in as Q times something? The free action.
So the Worldsheet action for the string
theory. I remember some statements, but maybe it was n equals 4 superheating mills, that some actions can be written as Q times something.
So some actions can, but not the open superstring action.
No, I meant n equals 1 superheating mills intendi, or n equals 4 in 4D, one of the two.
Okay, so there are different things that people do. So some things that people do is you start with some supersymmetric action, and then you twist the supersymmetry generated. So this capital Q at the moment has nothing to do with space-time supersymmetry. It's the BRST operator. But sometimes when people twist, you have a space-time supersymmetric theory, and you twist this supersymmetry generators, and you interpret one of the supersymmetry generators as a BRST operator. And in that case, yeah, some of these actions can be written on that.
Wait, can I ask a very stupid question about this? So we have this lambda, we get to just pick it?
So I've introduced it by hand.
Yeah.
So I've introduced it by hand in the following sense. So the BRST operator is this object times this d alpha.
Yeah.
So if I think of the BRST construction, the BRST construction is always a ghost times a constraint. So if you think of these capital D alphas as constraints, then this would be a normal BRST operator where lambda would be the ghost. But the problem is that these constraints are not first-class constraints because the d alphas don't all anticommute with themselves. And that's essentially what forces this lambda to be a funny kind of ghost that satisfies a pure spinor constraint. So it looks like a normal BRST operator, but because these d's are not first-class constraints, it's not...
Lambda is we're adding it as a field here?
So think of it as a ghost. So suppose, let's forget about field theory. We're just thinking about constructions of BRST. So if somebody gives you some system with a gauge symmetry, and we want to define the physical states, the gauge invariant states, Then there's a well-defined BRST procedure where you take the constraints and you multiply by the ghosts, and that tells you, you know, how to define the physical spectrum. So that's in the sense that I'm doing it here. I haven't told you, I mean, I haven't even written down the Super Mills action or anything. I'm just telling you by hand what it is.
So you made an ansatz for this vertex operator to be of the form lambda alpha A alpha, but what about other ansätze? Are there other physical states? Are there other states?
So there, for the other physical states, I have to build the string theory first.
So this board, sorry, are you describing just the ordinary open string theory on a 9-brane?
Yeah, but it's just the massless sector. So at the moment, it's just 10-dimensional Super Mills. I haven't said anything about, there's no strings yet.
I see. So then this Q lives on, this is an operator not on a worldsheet?
No, there's no worldsheet. It's just X's and thetas. So I just
so
have
this
the
is
zero
field
mode.
theory.
It's just a field theory. At the moment, it's just a field theory. So right now, I'm going to do the strings, but at the moment, it's just a field.
Okay, so this is a new way of formulating Yang-Mills, 10-dimensional Yang-Mills. In terms of, okay.
But can you calculate the correlators in this language?
No. This is just to get the right physical spectrum. So of course, to get correlators, you need to do string theory. So that's, and then of course you can compute scattering after using the string theory. You can see this one.
But isn't there an action which is Chern-Simons form written in terms of pure spinor superspace?
Yes. So, but the measure is kind of funny.
Okay, I see.
So he's asking if there's some kind of string field theory you can build for this. And there is, but the measure is kind of funny.
Wait, but I thought because the supersymmetry was on shell, you would never be able to write an action.
That's right. So the action is, that's essentially the measure effect. So you have to put in a regulator which creates the supersymmetry. Okay, so now the string theory. So, okay, so first we're going to do flat. And then of course the idea is to generalize to ADS5 times S5. So if we want to do flat, we first write down the actions. So the worldsheet variables. So I'm going to write it down by hand. And of course, it would be great to get it from gauge fixing some fully worldsheet reparameterization variant action, but in some sense, because we already have the BRST operator, I've already skipped that step. So I've already gotten to the BRST. And the action is very simple. So if we're doing closed string, you have double copies of this. But for the open string, you can just ignore this second step.
So this now is the worldsheet theory of a 9-brane.
So the 9-brane, of course, P and P bar are identified on the 9.
So this is an open string?
So it's open string if you put it on a 9-brane, which means you identify P and P bar
Oh, I
on.
see.
Okay, well, if you just ignore these, that's great.
But that thing is a closed string, the way you wrote
This is
it.
a closed string. So this would be type 2B because the thetas and theta bars have the same space-time chirality. If you were doing type 2A, this would have an upper index and this would have a lower index with the opposite chirality. Okay, so now we have a worldsheet field. And of course, we also have Q. So now we have Q, and I have to tell you what D alpha is. So capital D alpha is going to have to play the role like dd theta plus theta ddx. So if I think of P as being the conjugate momentum to theta, the obvious thing to write down is something like this. Because dx acts like ddx, it's like the conjugate to x, and P acts like dd theta. Okay, there's another term that's there, but okay, it's not going to play any role in what I'm going to say. I also have a term like this. Okay, there's some coefficients. Okay, so this is Q. This object here is related with D alpha. And similarly, Q bar. So this is the left moving one, the right moving one. Is the same thing, lambda bar alpha. And similarly, P bar alpha. Okay, so the claim is that the closed string physical states are states in the cohomology of Q and Q bar built out of these variables.
So P,
So lambda is a chiral field?
So lambda is left moving and lambda bar is right moving.
And theta is
Theta is left moving and theta bar is right moving. So this is of course in a flat background. In a curved background it's more complicated.
So P and theta are sort of like a BC system. Like a BC system, and with what lambda?
So this is conformal weight 0, this is conformal weight 1. So all of the variables here are either conformal weight 0 or 1.
Okay.
So that's nice because you don't have to sum over spin instance. And lambda gamma lambda is 0. Lambda bar is 0. And that implies there's a gauge symmetry, which is delta W. If you shift W by anything proportional to this, it automatically vanishes. So this is the gauge symmetry generated by this constraint. Simply delta W bar. So W and lambda, although it looks like they have 16 degrees of freedom, they have 11. So let's just count conformal weight. So you get plus 10 from here, you get minus 32 from here, and you get plus 22 from here. Because it's 11, you get 11 pairs. Okay, so there's no conformal weight.
That was the central charge you just.
Yeah.
So, sorry, those conditions, lambda, gamma, m lambda is equal to 0. What were they, please?
So this is the pure spinor constraint.
That's put in by, that's part of the definition.
Yeah.
And those variations were BRST variations? Those delta W alphas?
No, these are not BRST variables. These are the symmetries generated by this constraint. So you can think of this as a first-class constraint.
Oh.
So if I shift W by this, you find that the action doesn't vanish just because of the lambda gamma lambda.
So it vanish only if you require the first two lines.
Yeah. Okay, so now we can compute scattering amplitude in the usual way. We just have.
so the spectrum of this now looks like what?
Okay, so for the open string, now you're going to get. So of course the massless sector is just lambda alpha A alpha X theta. But then you can get for the massive, you can start having derivatives here. So you could have something like dxm A alpha m. So now it's a more complicated superfield. And of course you have some massive, k squared is no longer 0. So here's, I mean, I've taken the x dependence out and just to make things more explicit. So here of course k squared equals 0. This would be k squared equals whatever, 2 or something like that. So
And what about terms that don't involve lambda?
what is what?
I mean, vertex operators that don't involve lambda?
So all the vertex operators have to have ghost number 1. So the BRST operator obviously has ghost number 1.
So you look at the ghost number 1 sector, that's where your spectrum lives.
That's right.
So delta or W relations, those are gauge relations. You're going to gauge the.
There's a gauge, so what we're going to do is we're going to impose a constraint that W can only engage in variant combinations. Okay, so these are the physical states, and it's been shown that this describes the right superstring states. Now for the closed string, the idea is now you have lambda left, so you have lambda and lambda bar. Now your supergravity states are described by this multiplier. Okay, and this includes, of course, the graviton, but also the Ramon-Ramon fields, etc. So they're all contained in this superfield. And then you can, of course, also get the massive. So, for example, the metric sits at order theta theta bar. A alpha theta, and then the Ramon fields sit at higher order. Okay, so this is well understood, flat background. We can do scattering amplitude computations, everything agrees. You can do higher loop, etc.
I mean, that's just standard 2B in flat space.
Yeah. So
You can go to arbitrary loops, isn't there like some subset?
you can go up, so it's been done up to 3 loop 4 point, which is 1 loop higher than RNS. But going higher than that, there are subtleties that I don't.
Sorry, agrees with the free super young mills computation.
So we're not doing super Yang mills anymore. We're doing string theory.
Right.
And if you choose the states to be Yang mill states,
Yes.
then it's Yang mills interacting with all the superstring states. It's not just super Yang mills. It's all the alpha prime dependent stuff.
Sorry, agrees, you said agrees, so which two things agree?
So we haven't gotten to this picture yet.
Oh, okay.
To get to this picture, you have to first go to ADS5, which you haven't done yet.
Yeah, I think it agrees with the usual type.
With the usual
This
data.
is agrees with flat space NSR.
NSR. Everything that's been done on both sides is agreed. But there's no proof. So, that's something that needs to be done.
Both sides means like RNS or?
Yeah.
Oh.
So RNS has been done up to 4.2 loop with no fermions.
4.2.
Yeah, that's the
It's Docker.
Docker and Fong. And now there's a whole literature.
Sorry, why isn't it an integer? I didn't get it.
No, 4.2 loops. 4 point amplitude.
They did the calculation just one for two.
Sweep.
4.2. Trying 4.3 now. Epsilon expansion.
4 plus epsilon.
Okay, so now ADS5. Okay, so to get to ADS5, we need to perturb the flat. So we write down the flat action and the curve action. So the way to get the flat action and the curve action is to start with this action, and then you just add integrated vertices. Right, so it's just the usual. So what we've written down here is the unintegrated one. These are conform weight 0, or 0, 0. The integrated one you get from these are where this the Q bar and U is equal to dV bar on T.
Sorry, could I ask a probably vague question? On your worldsheet, X sort of corresponded to the space-time coordinate of your Yang mills. Theta corresponded to the superspace Yang mills. But lambda here corresponded to field in Yang mills, right?
So I didn't, we're not yet at ADS5 times S5.
No, I was just talking about
The theorem.
Uh,
n equals 1 Yang mills there in 9 dimensions.
So the way
In 9 plus 1.
I understand it is, this is just flat superstring,
Right.
and they're vertex operators.
Right.
And the vertex operators are these,
Right.
and there's no correspondence between worldsheet fields and.
But in the end, there's a correspondence, right? Because the A alpha of theta, you're going to expand.
You're going to say this is of course X. Is that the correspondence you mean?
That X, of course, is the space-time where you are in space-time, and that theta seems very similar to the superspace theta of your Yang mills theory, right? Or not?
Yeah. So this part I don't understand well. So I mean, I can speculate, but there's no. I would like to do what people do like with BMN, where you have worldsheet field and space-time things, but that's one step beyond it. I know. Okay, so the integrated vertex operator U.
It was just a field, right? And then
This is those numbers.
introduced a new field.
But it's only one. And the way you relate to it is this.
The question?
I don't even know.
I don't mind being
No, I was just asking Shiraz why he was saying that lambda corresponds to a field in space-time.
That's a guess. So let me just say where the guess comes from, because now that you asked. So the A's are supposed to be related to X's, right? And the phi is supposed to be related to the thetas. And when you look at the B field has a term X theta theta. So that makes me happy. But it also has a term lambda lambda XX, which I want to identify with this. Now, I can tell, okay, since you already,
Lambda XX? No, sorry.
this one is lambda lambda, so Okay, since you're already ahead of me, but I don't mind.
I guess your question should be answered in this
Yeah,
board.
on that board,
Right.
yeah.
I think the question should be about that blackboard, right?
I think, yeah.
Because it's about Hobbes' formalism and how Hobbes, or this P. Howe, I don't know how to pronounce that.
On the top
relates
right board,
lambda.
was lambda a function of x and theta?
That's what. It's
Oh,
not a function
so
of
then
x.
what-
Lambda is a worldsheet variable.
No, on the
No,
top
no,
right.
no, no, there is no worksheet. It's just about n equals 1 in 10 dimensions. Yes.
It's just a,
Variable, just like x and theta.
It's a variable. I
it's
see.
a variable. It's just a number. I
Oh,
mean,
I didn't
It's just
understand.
a worldsheet variable. It's not a function.
I see. So everything
It's not a
in
superspace.
10 dimensions is a function of x, theta, and lambda.
yeah.
Or
I mean, in this formalism.
So
yeah,
you think
the
of lambda as
a-
part of the space-time.
Yeah.
Lambda is a space-time direction in the field theory.
it's like a BC ghost. So if you think of what is B and C and
Forget the string theory. Just this on this point.
so it's
Yeah, we are talking only about 10D n equals 1 superior.
so suppose you're doing BRST just to understand the framework. So BRST, somebody gives you some theory, some gauge symmetry, and then you introduce ghosts, right? And the ghosts they don't depend on the x's and thetas or the things in the transform into the gauge fields. They're additional variables, the ghost variables.
No, but they usually fields. The ghost fields.
They're functions in, so these are
These are functions of x and theta? No, in 9 dimensions. There's no string theory.
No string theory. But aren't they functions of the fields of n equals 1 superior animals?
Mechanics, right? They're not fields, it's quantum mechanics. This is,
I-
the x's and thetas are quantum mechanical.
This is like a well-line formalism.
Yeah.
Oh, this I didn't understand. I thought you were doing a field theory.
No, this is first quantum.
Now I understand. Thank you.
Okay, everybody's happier now?
Yes.
This is just a baby version of what.
Now I
you
understand. I thought you were rewriting.
Yeah, it's
That's
just
why
a baby version of this,
Yeah.
where you.
That's why you called it open string theory. Because, yeah, okay.
Yeah.
Okay, sorry for the confusion. Okay, so now we're going to write down the vertex operator. So this is U. And I'm not going to solve this for you. This Q bar equals.
Sorry, I'm sorry to constantly interrupt, but is there? This suggests then there should be a way of writing just n equals 1 Yang-Mills theory in 9 plus 1 dimensions in a sort of superspace built out of x, theta, and lambda.
Yes.
That is possible.
So that's essentially what.
Short term. I see. Thank you. Now I understand it.
Okay, so d squared u. So d squared z of u is the closed string vertex operator, and it's related to this by this descent relation. And of course, as expected, you're going to get things like GMN, DXN, D bar XN, etc. And one of the things you'll get is F alpha beta, D alpha, D bar beta. So it involves lots of stuff. But the stuff that's most relevant for us is this last term here.
Now you're going to have curve space. So,
So we're going to curve space. So putting this in a curved background, if you think you want, you can think of it as flat space plus a deformation. So the deformation here, these are just the vertex operators for the graviton, for the Ramon field string.
The metric, yes.
We're just going to add it by hand. And as you see, if you put on a finite Ramon field strength, then you're going to generate a term which is second order in D and D bar.
So GMN is the perturbation to the metric.
Yeah.
It's not the metric.
Right. So it's like I call it HN. But then, of course, I can put all this together into some covariant form. So this is going to become the AJS left times this 5 action. Okay, so now, one thing you can see immediately is you can integrate out D and D bar. So actually, I could have written this in terms of the D's too. Yes? If I do this, these will get modified. This will become, there's some theta dependence here, but let's just.
Sorry, you put this and then there's a beta function condition that gives you some equation for H and F?
No, so I put this, if this vertex operator is BRC closed,
Okay.
and to linearize the order,
So you modify the BRST operator, or that stays fixed?
so the BRC operator will always be lambda alpha. Okay. So,
But you replaced P alpha by P bar. What did you do there? You integrated out?
in a flat background, P alpha is a free field.
Yes.
Once I work in a curved background, there's no advantage to using P alpha or D alpha. They're of course related.
Okay.
The advantage of using D alpha is that if I do a space-time supersymmetry transformation, D alpha is invariant, whereas P alpha is not. So you can write these objects. Right, more carefully. This is pi m, pi bar m. The pi m is supersymmetric version of dx. So these are details, but I don't think these details are so relevant in the moment. But the idea is that in the end, you can write the action in a curved background. In terms of, so let me write this general function. GM where Z can either be X's or thetas or theta bars. And then you have terms involving the D's, where you have things like D alpha, E alpha M, D bar, ZM. So now I'm writing the most general supergravity background. And then you also get terms involving F alpha beta. You just write down everything you can which has the right component. And finally, you also can have terms involving the ghosts. So the ghosts have to be introduced in a way which is preserved under the gauge symmetry of W. So the things which are preserved are the Lorentz kinds. So NMN is W gamma M lambda and M bar. These objects are gauge invariant objects you can construct out of the lambdas. Okay? So they're the analog of the psi m, psi n in RNS. So you also get couplings of the type R, MNPQ, MMN, and bar PQ. Just like you do in RNS, you get couplings of the left and right moving psi's to the curvature. Okay, so these are the type of terms you're going to get in a general background. And of course, for this to be BRST closed, you'll find that all these background fields have to be on shell. And that goes to your beta. So that's classical level, then you have the quantum level, etc. So we're going to concentrate on ADS. So in ADS, 5 times S5, this is just going to be gamma 0, 1, 2, 3, 4 alpha beta. And this is just going to be the ADS 5 times S5 curvature. So this, now, if you know Green-Schwarz is just the first term. Okay? So Green-Schwarz has the property that it's simple, but it has kappa symmetry, so you don't know how to quantize. This action doesn't have kappa symmetry, but it has this BRC symmetry. Okay, so now ADS, 5 times S5 finally. So S is equal to, so I'll use the notation which is common, you know, if I could explain what it is, people don't know what it is. R squared. These are terms in like in bar. Okay, so the J's are built out of these methylcycline-like. So now we're switching gears to ADS5 times S5. So we have
No. Equal to.
Equal to.
S equal.
Oh,
Yeah, this is me. PS324, ADS4, and S5. So you can think of it as a block matrix. Now here you have the ADS5, here the S5, and here you have the 32 states. So it's an 8 by 8 matrix. So this is what and the way you realize the coset is that you identify G with G omega. So you think of G as this is G. And you identify G with G omega, where omega is in SO4 1 times SO5. Omega would just be a block diagonal where these elements are in SO4 1 times SO4. And the PSU24 generators, so the global PSU24, it just acts on G by multiplication on the other side. That would be the PSU. Okay, so one thing I didn't tell you is when you get to this, so this action here, of course, doesn't depend on the D's. Just depends on the X's and thetas. So I can tell you what the J's are. So you define J to be G minus 1 dG and J bar and G minus 1 bar G. So these sit in the Lie algebra. And they're, of course, invariant under the global PSU24 by construction. Well, I should have said, sigma is just constant because it's global, right? But this omega is not constant. This can be a function of x and theta. Okay, so these are left invariant forms. And of course, they sit in the Lie algebra, so the way we define them is we put J2 here, and this one is J1 plus J3, and this is J1 minus J3.
So it's a graded algebra, and you then split it into J1 plus 2 plus 3.
That's right. And J0 is the elements in the SO4 1 times SO5.
Where was J0? Which J0?
So J0 doesn't appear in the
Ah, okay.
It appears, sorry, in the covariant derivatives. So W del bar lambda is really W d bar lambda plus W J0. That's the, so this would be the connection which transforms covariantly under the local SO4 and SO5. Okay, so it's trivial to show that this is PSU24 invariant. The non-trivial thing to show is that it's BRST invariant. Okay? And that's what's going to determine all these relative coefficients. So as I said, in
In
short,
this language, the BSD operator is what?
so after integrating out d alpha, what you find is that Q becomes just one of the currents. So it's lambda alpha times J3 and Q bar is lambda bar alpha times J bar 1. And you can show that these are holomorphic and anti-holomorphic currents using the gradients of motion. So,
The alpha component of J3, where does this come from?
so J3 and J1 are the fermionic PSU24 generators. And you can either write them as these 4x4 matrices, or you can combine them into this 10-dimensional spin.
Why it couples to an 11 dimension? I mean, the lambda is still a pure spinner? Or?
Yeah. So what's the question?
So lambda is 11 dimensional, but J3 is 10 dimensional? Or?
Sorry, actually I say lambda is 10-dimensional.
Okay. And the J3 is also 10
alpha is still 1 to 16.
Okay.
Yeah, it's 11 component, independent.
It has
11 it's 10-dimensional spinner.
I see.
So alpha is 1 to 16 always. Okay, and again, q squared equals 0, using the same argument as before. You have to know how J3 acts, so it essentially does a rotation. So how does the BRC operator act?
So when you write J2 in the diagonal, you mean they're just different components of J2?
Yeah, so
J2 has components in the ADS5 and components in the
So the Lie algebra here, this is
the SO4,1 and the other one is SO5, SO6 and
SO4 to divide it SO4,
SO6,
exactly. So this is SO6 over SO5, this is
SO, yeah.
SO4 over SO5.
Okay.
They're both called J2.
I'm sorry?
They're both called J2.
They're both called J2. And
Okay, that's good.
They sit in this vector. So the language J1, J2, J3, J0 comes to this because there's a Z4 grading.
And
But,
is there
I
a reason
mean,
why you...
J2 is what we would normally call the position in ADS5 terms. That's
Right.
So it's like dx.
Oh, it's like dx. Oh.
So one is the stabilizer, and the other one is what takes you out of it, right?
Is there a reason why you pick J3 for Q and J bar 1 for Q bar? Why don't you pick J3?
So when you integrate out d alpha, you'll find that d alpha, you get the equation like d alpha so you get something from the f, so I guess like fd is equal to something like e alpha m. Oh no, because this is an upper limit. F alpha beta d beta is equal to something like e alpha m e bar zm dzm. You'll get an equation like this, and this becomes these j's.
So in the upper left block, there are 15 J2s.
There are 5 here and 5 here. So you start with 15, but 10 of them
I'm modded out. But in your formalism, okay, so you've already, the J2 is modulo J0.
The J2 is, that's right. So there's no J0s here because remember this is an action which is in the coset.
Right.
So if you put the J0 here, it would not be, it would be the full group. That's not what you want.
Right, I thought you were going to write an action for 15 and then gauge the remaining.
Yeah, you can come with that. So if you go to the flat space limit, it just becomes the usual dx d bar x, if that helps. Okay,
So if I were to just have written lambda alpha J1 alpha on the left, does that have some nice property?
Not be holomorphic, no. So J3 turns out to be holomorphic. So remember the thetas were holomorphic and the theta bars were anti-holomorphic. When you go to ADS 5 times S5, it turns out J3 is not quite holomorphic, but if you contract it with lambda, it is holomorphic.
Oh.
But if you contracted J1 with lambda, it would not be holomorphic.
J bar 1 contracted with
J bar
lambda
1
1.
and lambda bar is. So there's a Z2 symmetry, which is if you switch lambda and lambda bar, and you switch J1 and J3, then the action is inverse.
So even though you don't have like a Wieso-Minowitten-like model, but nevertheless these contractions are holomorphic.
So you can't write holomorphic currents directly.
Yeah, because you don't have a Wieso-Minowitten-like.
Leave the lambdas to make them.
I see.
So this is then a chiral U1 field, or I mean, if I didn't integrate it,
This would be, so this is a conformal weight 1 comma 0. That's what you're asking.
and the OBE would just be like a free boson.
So it has ghost number 1. Well, I'm not sure what you're asking, but it's holomorphic, so it doesn't have any Z bar dependence, if that's what you're asking.
But the double pole is 0 because
It with itself, the double pole is 0, yes, because q squared equals 0.
So, sorry, please, a naive question. It looks, the theory you've written down looks very complicated and non-linear and interacting.
Yes.
How are you able to conclude that q square is 0, for instance?
Okay, so I know how the BRST operator acts on the field, so I didn't tell you that, but let's do it now. So I told you how the global symmetries act. How does BRST act? So the way it acts is very simple. It takes delta BRST, G is equal to G, not times omega, but it's equal to lambda alpha times, I'll call it T3. I'll tell you what these are in a second. Plus lambda bar beta T1. So these are the PSU24 generators in the fermionic directions. So T3 is like this plus this, and T1 is this minus that. So it just acts by multiplication on the right by something which is not an SO4 1 times SO5, that would be a gauge, but something which just involves the ghosts.
And sorry, you know that because you know the OPE of J3 with something else?
Yeah, you know the OP of Q with.
I want to know how you know that.
So you can start with, okay, how do we know it? Okay, you could do Poisson brackets if you like.
Is that reliable? It's an interacting theory.
I think it is because these are homomorphic, so nothing can be deformed. But okay, let me try to make it more explicit.
So they meant in your variation of G, is that meant to be a T or a J?
T, it's a T. So T, my notation is, I'm probably not using the best notation, but the J's are these G minus 1 DGs, and the T's are just matrices.
The generators of the Lie algebra.
Generate the PSU224 transformations.
Oh, I see. Okay.
So for example, the omegas, what I mean by omega is this is the quantum that's about 10 times, of course, the generators in this. Okay, how do I know this? So I think you can go backwards and say, okay, this is the definition of Q. And with this definition, the action is invariant.
You wanted an explicit operator that implements this definition.
Well, that just comes, now I can use the Noether method, once I know the symmetry.
Noether method sounds classical.
Yeah, okay, so, but now your question is, are the quantum corrections?
Yes.
So I have a paper on this discussing possible quantum corrections. If you want to preserve PSU224, there's nothing else you can write down. So in some sense, you could write down, for example, the most general action, which is PSU24 invariant.
I see.
And then you could look at the coefficients.
I
See if any of those coefficients can be.
So ADS is such a symmetric space that classical is the only thing you can
The
do.
only thing you can do is change the R squared. Essentially, there's nothing else you can do.
So, is the question about anomalies, like whether this?
Yeah.
Okay.
So that's essentially the way you answer it, is by looking at what possible terms you could add with your PSU24 invariant. Essentially, it's so restricted that there's nothing you can do. Okay, so now we've gotten almost to the stage where we can compare with this. The next thing to do is to write down vertex operators. So we have the BRST operator, we have the action, and now we can ask, okay, how do we describe the physical states? And the short answer is that I can only do the half PPS states with confidence. Okay? But once you do that, there's a guess about the non-BPS, which leads to this conjecture here. Okay.
They wrote the same Q.
So this is the R squared. I mean, going back to the first blackboard,
Yeah.
this is like the R squared term, right?
So I haven't.
What about the
So right now, this action is everything. Okay? The claim is that this action here can be decomposed into two terms. One term which is symmetric in Z and Z bar, which is essentially going to be this BRST trivial term, and the term which is antisymmetric in Z and Z bar.
But the whole action is proportional to R squared, so your first term would also be proportional to R squared?
But as I said, the coefficient in front of the first term I can juggle as I want. So I can take that to be 0 if I want, or infinity. So,
But are you going to explain what the first term will look like? Or?
yeah,
Okay.
it's mess.
Okay.
Okay, so first the vertex operator. So as I said, what I'm doing now, I can say with 99% confidence everything is correct. But at some point,
Little a is a function of R.
in the end, what I'm going to want to do when I do the topological string is take A to infinity. Because what that's going to do is going to force my worldsheet to be, to suppress everything except for the classical solutions. But obviously, yeah, at the moment, if I do small radius, this becomes small, so that's not what I'm... Okay, but we're not there yet. Okay, so the first thing is to write down the vertex operator. So we need, obviously, Q, V equals Q bar, V equals 0. And there's one case where we know the answer quickly, which is the vertex operator associated to the radius modulus. So the Lagrangian, you can think of as the closed string as a closed string vertex operator. And the unintegrated vertex operator, that it's easy to compute. And you just find that V is equal to lambda alpha. So 1, 2, 3, 4, lambda bar. So it's this operator here.
Sorry, you're saying Q with that will give you the Lagrangian?
So if you take, if you take Q bar on the Lagrangian, you get DD bar of this operator.
Oh, I see.
So remember the relation is Q bar on U is equal to DD bar of V. Okay, so that's very simple. But now we want the vertex operator for more interesting states.
What is the x? There's like some e to the ik.
Sorry, this is the radius modulus. So there's no, it's just a, it's a constant.
It's
Doesn't
just a
depend
zero
on.
model.
So, but U is not easy to write down.
For this state, U is just the vertex, it's just the action.
Oh, you're saying, okay.
So this is essentially the only state which is easy. Now the ones that are interesting are, of course, the ones, so this is not even the singleton, this is the zeroton, or whatever you would call it. It's the state which has no excitation. So, of course, what we want to do is something like this state here. So these are the half PPS. So these would be the analog of the supergravity states if we were in a flat background. Okay? So you want the ones which are dual to this. Okay, so the way we're going to do this, so I'm going to tell you the answer and then I'll try to explain where the answer comes from. So to define phi, you can think of phi as being determined by an x and y on the boundary such that x squared equals 0. So x now has, I don't know what kind of notation I'm going to use. So let me use this notation. So j with a equals from 1 to 4. And R and S go from 1 to 4. And this is antisymmetric in J and K. This is antisymmetric in R and S. And if x squared and y squared equals 0, then these are points on the boundary of A ds 5 times S 5. If they're equal to 1, then they're in the bulk of the A ds 5 times S 5. Okay, so any questions about that notation? Okay, so the term we're going to add is going to be something like x. So capital X is equal to capital Y squared is equal to 1. So these are in the bulk, and these are on the boundary.
So basically, if you are in the bulk, you have rescaling symmetry, and you can always choose it such that this is true.
Yeah. So, okay, I think, yeah.
So, sorry, I understand that the boundary is special for X because we're going to the boundary of embedding space. Why is the boundary special for Y?
Yeah, so that's kind of, so Y of course has to be complex, small y, because it's just Euclidean. And it has to do with the choice of, for example, a null vector, which tells you, for example, if you're doing trace, so these phi's, if you think of them as scalars, they have to be null.
You want to make it BPS, you're saying?
Yeah, so they all need to have
BPS.
the same arc charge.
The BPS, the tracelessness condition.
Yep.
Is this Y thing? I understand.
And why are they symmetric, not skewed?
I'm sorry?
Why are x and y not?
Also antisymmetric. So it's,
Sorry?
there's 6 of them.
Oh, they are. Sorry, I was reading those as symmetrizers.
So this means antisymmetric.
Oh, sorry. Okay.
But why is the tracelessness condition special on the boundary rather than everywhere? I still haven't understood why there's a boundary in this space, in this Y space.
I mean, you know this stuff better than me. I mean, I don't think of why is there a boundary of the S5? That's what you want to
Yes, I mean, the S5 is S5 everywhere, boundary and bulk.
So you have to some kind of
Complexified. So,
Okay.
but you're looking at some complexified y. So it's like a hyperbolic space.
So if you want to think of
Real
y,
numbers.
so let's say it this way. Forget, if you want to think of this, just some small x's and small y's, which are used to define the physical states of being mills.
Yep.
And the capital X and capital Y are a ds 5 times s 5. So don't, maybe boundary is not the right word. Just, then the dependence on capital X and capital Y here is just going to be
Right. I think yeah.
Is that x squared is equal to 0 for BPS states?
Right.
And is anything else for not BPS
Exactly.
states?
So I'm only discussing half BPS states at the moment. Okay? So this would correspond to the state trace of phi to the delta. But this is not yet, so this is, you can think of this, I mean, I don't know how familiar you are with this, but this is like the bulk to boundary propagator agent.
So x and y are specifying which operator, little x and little y are specifying which operator and where it's inserted, and capital X and capital Y are the wave function for it, coordinates of the wave function.
Variables. So capital X and capital Y are these variables here for G.
Okay, thank you.
But this is not BRST invariant. Okay? If you do a BRST transformation on capital Y and capital X, it's not 0. So you have to add something else, and this is the part which took a bit of time to get understood. But if you take small x slash small y, these are x squared. So these essentially choose a set of the, so you have 32 thetas. And using small x and small y, you can choose a set of 8 thetas out of those 32 thetas. So if you're familiar with PSU 224 written in terms of PSU 112, so this is the usual, it appears in BMN, I mean it's been around for a long, long time before BMN. What you do is you just split the 4 J's and 4 R's into pairs of 2. Okay, so you split J into, let's call it small j and j bar, and R into small r and small r bar. And these transform under one of the PSU 112s and these under the others. And the 8 thetas that this is going to choose is essentially just the thetas with j and r. That would be the 8 that it chooses, the 4 that it chooses.
These are the ones that transform under one of the PSU 1,1/2s, but not the other?
So the J's transform under one of the PS. Yeah, you said it right. I said it wrong. So the bars transform under one of the PSU 112s and the unbarred under the other one. Okay, so what I want to say is that choosing a small x and small y chooses 8 of these 32. And you need to have all these. So that's what I mean by this notation. And it's still not BRST invariant. You have to put in delta of Q. So let me say what. So Q of theta, if you go backwards, Q of theta is something like lambdas. So these are something like x slash. So you have to fix 8 components of these lambdas to be 0. And these, so this is like, obviously, means that. So what does this do? This means if you take the BRST variation of this, you find that it always has terms which are either proportional to theta or to Q of theta. Let me try to say it. It's better.
Vanishes.
You find that there are always terms which are proportional to x slash theta y slash times delta, or things like x slash lambda. So this just comes by analyzing how the BRST operator acts on this. I don't think I have time to go into detail, but this is completely straightforward. all you have to do is decompose the PSU24 under the PSU112 and see how the different things transform.
So this delta is a Kronecker delta or is a delta function?
I'll tell you what it means in a second. So it's delta in the sense of Friedel Martin Schenker. So you think of bosonizing the lambda. So let's just take one component of lambda. Let's call it lambda 1. And you write it as a to 1, e to the phi 1. And let's call it w, which is the conjugate to it. So I think of this as my beta gamma system of Friedel Martin Schenker. And then what I mean by delta lambda is just going to be e to the minus phi 1. So if you're not, so in some sense it's like a holomorphic delta function. So it's schematic, and obviously in the end I'm going to have to do something with it to get rid of these deltas, and I'll tell you what that is in a second. Okay, but, before I do that,
But it is just setting lambda 1 equal to 0.
sorry?
It is just setting it equal to 0.
It's setting it to 0, holomorphically or whatever.
Yeah.
So this would be the analog in RNS language of the vertex operator in a picture. So because it has explicit e to the phi dependence. We want to get rid of this. Okay, so this is not yet the final form.
So you've picked a certain PSU 1,1/2 squared inside PSU 2,2/4, but there's a whole.
Right, so this is just one state. So this would be the state for specific phi. So suppose it was, for example, trace of z to the n. And that would be a specific choice of small y and small a. If I want to choose any of the other scalars, I just rotate the y's and x appropriately. And of course, you can get other elements of the multiplet by hitting with the supersymmetry.
So the BRST variation of this factor, y dot y by x dot x, that was x/theta y plus.
This thing here?
No, the next.
right.
Oh, so if you take the BRST variation of this, there are all kinds of terms.
Yeah.
You get the BRST variation of the y, of the x,
Yeah.
and you find that all of the terms are either proportional to one of these thetas, one of these 8 thetas, or proportional to one of these 8 lambdas.
So you kill everything except the first one.
I see.
So that's why this construction gives you some BRST invariant.
So this big operator is it would have dimension 0, for instance.
It's dimension 0, it's conformal weight 0. So, of course, there's no, because of these small y squared and small x squared equals 0, these have no OPs with themselves.
Okay.
The worksheet.
I don't know how to answer your question in a concrete way, but I think,
Yeah,
yes.
it should be dimension 0, yeah. Okay.
Okay, so this is not the final answer because it's in a picture. Okay, so we want to convert it into a vertex operator which is in a 0 picture. And now there's a prescription with it. So it's like picture changing in RNS. You multiply by, let's call it P. So PV would be equal to the same P, but now we're going to multiply by the product, I'll write it like this, Q of P. So you multiply by 8 picture raising operators, where the X's are just the conjugates to these etas. So you have 8 of them. And what happens is that when you compute this, so Q of V equals 0. So let's do it one at a time. So you have something like Q C to the 7. And then you have Q of one of the X's. So there are 8 different X's, so this is just one of them. Let's call it C1. And now you see, because V has a term proportional e to the minus phi 1, this is going to be something like Q of C1 e to the minus phi 1 times other stuff. This object here is 1 over lambda 1. So now we know how Q acts on this. So this object here, you've written it just in terms of the lambdas and the thetas. So we know how these things transform under BRST. And now you can show that because this object has to be BRST closed, this has no poles when lambda 1 goes to 0. So the way you argue that is that if you peel off, you know that this is BRST closed. So if you peel off one of these delta functions, you know that the BRST variation of everything left has to be proportional to the lambda that you peeled off. So that means the BRST variation of this stuff has to be proportional to lambda 1. So that guarantees that the pole cancels. So after doing all this, hitting, with all the 8 different picture changing operators, then you get something which is in the 0 picture.
Which means removes that delta function.
That's right. So all the delta functions go away. Now you just get the polynomial in terms of the lambdas and thetas. Okay? So this was explicitly computed by Flordy and Martin. So it's a mess. So the simple answer is this, but the thing you need to really use is this. Okay, so now we're at the stage where...
so it's the 0 picture thing that you will exponentiate.
That's right. Okay, so that's the vertex operator, which is going to come in here. Okay. Okay, so now we can go back to this picture. So what
You can write down an explicit formula for it, so it removes the deltas, but it produces all sorts of other terms.
Yeah. So for the half BPS, they use Mathematica, of course.
But can you work out the OPEs of the resulting vertex operators, or is this?
No. So the action is complicated. So, but at least we have the expression for the half BPS vertex operator. Okay, so there's a nice way to write down the expression, which generalizes easily to non-BPS. But it's just a generalization, speculation of what the non-BPS would do. So what you do is you take lambda bar. Now I write this, instead of writing this all at the same time, I write it like this. I write y dot y x dot x times this theta to the 8 delta of q of theta to the 8 times p. But I just, instead of having w factors of this, I just do one of them. And then I do it again. Y dot w over x dot x. Dot, dot, dot. So if it was w equals 2, it would stop here. And now why is this the same as before? Well, the picture changing operators, in some sense, you can put wherever you want. So these picture changing operators are obviously going to kill this kind of thing. And then you're going to be left with the original term where this becomes a square instead of being 1. So I think of this as being I call this object, let's call it E. So you're going to get E1, E2, E3. And here we're going to have these picture changing operators. So the picture is, if all of the E's are the same, it's half BPS. And that I think, there's no question that this gives the right vertex operator. The conjecture is that for non-BPS at small radius, or at 0 radius, this is the vertex operator. So now will you choose these y's to be different? So now this is, of course, no longer half BPS.
So the choice of the y's also determines how you break the PSU2,2/4 into PSU1,1/2 square.
Right. So each choice of the small y's tells you which state. So if you were doing trace, for example, of Z, Y, Z, W, right?
Right.
So if they were all z's, then all the y's and x's would be the same. But if I start putting them at different points or in different
But
rotations.
also the x dot x slash theta y slash term, that depends on which.
That's right. So this term here is what I'm calling E. So the choice of which states you put here depend again on this choice. So
You rotate it and then you.
Yeah.
So now this is speculation. Okay. So.
But each of these it's only the correlator which is not protected, but but individually the states are all half BPS, right? I mean, so
No, if I choose different y's, these are no longer half BPS.
Yeah, you can rotate one of the y's to become a z and a z bar, for instance.
This is not half
But
BPS.
I thought, no, I thought you're considering trace phi to the W.
So this one is.
Then you would
BPS.
put, yeah, so that's half
Here,
BPS.
There's only one small y and small ones
Yeah,
here.
oh, that's not what you're doing here.
Right, now, so if all of these y's and x's are the same, then it's half BPS.
So
If you take only one of them, you get away
Now
from
allow it
BPS.
to be different. So now it's a general.
So that's okay.
So now I have a conjecture that this is the vertex operator at 0 radius for arbitrary.
Okay.
Single
So
trace states.
okay, I misunderstood. I thought you were taking a correlator of the half BPS operators.
No.
No, you're just generalizing to
So
the
first step,
non-BPS.
just write down the most general, try to write down the most general vertex.
Okay.
It's basically a product of what looks like the vertex operator for W equals to 1, but rotated relative to one another. And that doesn't look like, I mean, why is it not trace Z times trace Y? You're saying it has to be single trace?
Just single trace. Yeah, I think the string, I think the duality with ADS-CFT.
But I mean, as a vertex operator, it looks like the product of two things with smaller W, doesn't it? So it looks a bit, it seems a bit funny that it reproduces the trace condition of the combined object.
So it's 0 radius. How do you determine if there's a single trace or a double trace? I mean, there's nothing pulling the states together, right? Because you have 0 radius. So
No, but
N is large, right? You are telling that N is large.
n is large, but I mean 0 radius. So it's 0 tension.
Serious radius is not G N equals equals 0.
Sorry, but it's 0 tension, right?
But the number of traces is conserved at infinite n, regardless of the
Right.
Yeah.
Okay, so you say that at 0 tension, the string somehow, this bit somehow knows about the other bit.
the ordering should be,
The contractions.
yeah, the ordering should be there.
Okay, so
And maybe it's a linear combination actually of single trace and multi traces. Right?
this is what I want. I say what I want is that it's single trace. You ask me why does it stay single trace? That's what you want to say.
What's the distinction? How do you distinguish between a single trace and a multi-trace?
On the worldsheet, you should only have single trace operators.
So
Yeah, but it's a bit funny that you multiply
It
two
looks
vertex
like
operators
you are
together that were
considering
separate traces.
The product of two single.
Yeah, why do you say that? Say that a little
Well,
more.
because I mean that's what he does. I mean he writes down the vertex operator for the first, and then he multiplies essentially, except for the lambda bar term.
but I could even say it for the half BPS. So suppose we look at half BPS.
I believe anymore.
How do you tell this half BPS state from the product of?
And besides, where is the cyclic ordering?
But I could ask that from this state also, right? The half BPS. How do you see that this is?
But there, since it's all.
Well, no, actually you can ask the same question there because there are double trace which are multi-trace, and in n equals 4 it's hard to distinguish those. So let's say length 4, you have trace of z to the 4, that's BPS, but also trace of z squared is BPS. And it's hard to distinguish.
Okay, so I think I'm.
That would be a two-particle state. So
Well, actually,
there wouldn't be a
at
vertex
large,
operator.
at large n, they don't mix.
Yeah.
As soon as you put 1 over n corrections,
Yeah,
they
but-
start mixing, and the
Right,
two-particle
right.
state is not just the first one. It's not the second. It's
But
some-
let's say I think he's working in the limit where
right.
at infinite n.
Part of this is ansatz, but I'm trying to solve this equation.
I think the question, Nathan, is that here, when you want to identify with this single trace Z, Y, Z, there is some cyclic ordering. How do you see the cyclic ordering in your vertex operator?
Okay.
This was not clear.
So again, this is speculation, but if I chose a different cyclic ordering here, then because it's non-BPS, these vertex operators do have OPs.
Right. It's just the ordering of the operators.
Right.
So the
So you're saying
ordering there,
His product ordering is
And that's something you can count.
But that's not cyclicity, like if people are asking, I think that it's just like, so when you write a vertex operator, you start from some field, right? And then goes around this race, but you can imagine starting from other.
So
But-
what I'm trying to say, I think some of you follow what I'm saying, but
Oh,
the
okay.
idea is that if suppose I try to switch the order, not the cyclic order. but the order,
Okay.
then the point is that the vertex operator is different because these have OPEs. This has an OPE with it.
Yeah.
So if you switch the ordering, you'll get contribution from that pole.
Right.
But if you do a cyclic ordering, if you change all of them, then that shouldn't change.
But that's not obvious from the
Yeah,
vertex
yeah,
operator
that's
you've
not
written
obvious from
down.
the
But because in the vertex operator you've written them down in a certain order, right?
So suppose I take, so suppose, forget about ADSR times SR. Suppose I look at the operator coming from taking the OPE of these three vertex operators together. If these start like poles, then I have to be careful how I take the OPE together.
Right.
But I think if I just do a cyclic rotation, that doesn't do anything. That won't change the state.
But in the formula you've written down, so you're saying there's
So I think write it down in a careful way. When I wrote it down, I meant that they're cyclic.
Some point splitting that you're doing.
So I'm putting these at different, slightly different points on the worldsheet,
Right.
Okay.
where the points are.
Cyclically, okay.
and you're saying there are funny poles and you have to regularize it and there is some point splitting procedure.
Okay. And that's the
Choose
trace, then
one.
you recover a single trace level.
So if it's half BPS, of course, you don't have to regularize it, so it doesn't matter about the ordering. But if it's non-BPS, then the ordering matters when you take the, when you try to get the OPE that's coming together.
And you're saying you take these points, these guys in a certain order, and you bring them all together.
Yeah.
But if you brought them all together from the other side, you took it around the circle, you would get the same thing.
Yeah, though it's not completely obvious to me that for an endpoints, I mean, when you have n, that it's only a cyclic ordering that will matter, because there could be multiple ways in which you bring them together. And
Yeah.
I mean, also if you put new,
That's true, but there are different, sorry, so suppose we have more than three, so this is.
right, but what?
Well, okay, then, yeah, there's more than just two ordering, so A, B, C, D would be different from A, B, D, C, for example.
Yeah,
No, but Rajesh is asking, why is ABCD the same as DABC?
Oh, but that's just a rotation.
I mean, when you define the vertex operator, are you summing over all the cyclic orderings? I mean, they're standing in a certain order as an operator product.
I guess the question is the
I'm
following.
taking it around. Right?
Yeah.
With the question of whether that changes anything.
We see what you are saying from the pictures, but not from the definition of the first line.
Yeah, so this is solid. So what I mean by this is taking somehow, for example, first taking the OP of this with this on this side, and then.
Right. And then you do that in order.
And then you sum over all the cyclic orders, or?
I think so. First,
No, I think it's automatically.
is that automatic?
It's not automatic.
It seems to be the question of whether if you've got these guys together, now you take this guy from the right and bring it back to the left, whether you get the same thing. Because you want in the end to find the operators where they're all at the same point. Right. So you could put them on the same point like this, and then if you do this, that generates the cyclic things. And the question is whether that changes anything.
I don't know the answer to this, so I'm just giving my speculation.
Yeah.
But it seems reasonable to me.
I mean, this is a well-defined problem in open strings. It has to do with the compactification of the modular space of the disk. There are certain prescriptions how to approach in a nested pattern infinity.
And it might be only true up to something which is BSG trivial. So remember, this is topological, so there are all these additional gate symmetries that may, identify different states which look different by something which is BSG trivial.
So ideally, one would like to make a counting of how many things are different and make a counting in single traces and see that the same.
But now it's clear that it'll work, right? I mean,
It's clear that it should work.
now because it's the same as the Engel's problem, more or less.
Yeah, okay. So that's part of this conjecture, of course. So that now the thing is that since you have, so I'll need about 5 minutes.
So how do we know the scaling dimensions, the field theory scaling dimensions corresponding to these?
So in zero radius, it's trivial. Zero radius, it's just the sum of the.
No, we know that from Yang-Mills. How do we know that from the string theory?
So that should come from the fact that it's topological.
Okay.
So it shouldn't matter how close the things are to each other.
It's a zero mode action of the global PSU symmetry, right? And that normally doesn't. That should. I mean, for that you don't even need topological, I guess.
Well, but I mean, they're OPEs. So as these approach each other, you might get some renormalization of those things, right? Because you have singularity, so you have to subtract out the singularity. So
Are we talking about worldsheet or space-time dimensions?
space-time dimensions, right?
Space-time
That's
dimensions.
just calculated on the worldsheet.
Right, but so for half BPS, of course, it's trivial. For non-BPS, if you were non-zero radius, then of course there would be corrections. So the point is that if it was topological somehow, they become, that helps you. Okay, so what's this idea about this? So, again, this is just pictures, but the lambdas are going to be somehow related to where you are, if you're near the boundary or not. So the point is that these objects here, the claim is these objects here are going to pull you near the boundary.
Sorry, Nathan. Do you think it might be possible to do instead of looking at vertex operators, compute the partition function of this? I mean, compactify time, which is some part of your PSU2, PSU4, part of your system. Overfold that theory by time and compute the partition function.
So maybe not for me, but maybe for somebody else could try to do that. I just don't have much. I don't have much familiarity with these topological strings, but.
You would first go to the Euclidean
Yes.
version?
Go to Euclidean. That would be extremely convincing, right? If that gave the free angles partition function, that would be extremely convincing.
Okay, so let me just say some other things about this picture, which again might be useful for other things that people are doing that might have nothing to do with pure spinors. But so the action, of course. So I didn't tell you what lambda is. So lambda is a mess, but okay. So lambda has things like. So it's obviously ghost number -1 because you want Q of it to be ghost number 0. So that means it has to have inverse powers of lambda. That's the first thing that should scare you. So,
But does it look anything like a free theory? I mean, as Rajesh was saying yesterday, somehow wouldn't we expect the worldsheet theory also to be free for free Superang mills?
So you can take if you take A goes to infinity, then you can take the limit in which you rescale out all the terms which are not quadratic, and then you get a free field theory. Yes.
So it's free fields in the lambdas and in what?
Yeah. So you get some. You'll get something like this kind of thing.
It looks like the flat.
There might be some other. Sorry.
It looks like the flat superstring again, or?
Yeah. So there. So again, it looks like this because if you take A to infinity, it looks like the large radius limit, which looks like flat. So this is not the full. This is not the full superstring action. So.
But then what Shiraz was asking earlier, that it would then seem like if you were to compute the partition function, it would be that in flat space or with a thermal
It's not quite flat, so you have different, remember there's a P theta thing in flat space. So it's not quite the flat space. So maybe there's a simple way to do this. I mean, as I said, I just don't have any familiarity with this. So, yeah, so if you take so lambda is complicated. It involves things like lambdas and j's and inverse powers of lambda. Okay, and then after you do that, you're just left with something which is antisymmetric in Z and Z bar. But there's something that I forgot to say. So it's the ADS 5 times S5 metric. So you don't just get dx
Sorry,
divided by the Z squared.
you have the right, yeah.
So it looks like the sigma model on.
Sort of a classical sigma model.
Yeah. But it feels like you'll then get the supergravity spectrum. I mean, if you were naive, right?
Well, it's not quite, so as I said, it's not quite the flat action.
It's not quite the flat action. I see. You see, A, because the metric is renormalized, is that of ADS, but B, there's a second difference as well. Right.
This counting is very similar to a problem that Weissert and Bianchi tried to do like 20 years ago, where they wrote the spectrum of free n equals 4 superior mills, and they tried to match it to the spectrum.
Yeah.
I think it was flat. They were trying to use the flat strings on that
I know that paper.
case, and it kind of didn't work, or they were so maybe this kind of
Awesome.
solves the problem.
Fixes it, yeah.
Okay, so I'm running out of time, so I have to think what I want to say. So, this has a property that as z goes to 0, z equals 0 means near the boundary. This would freeze out. So you have an a here, right? So naively, as you take a to infinity, this should become quadratic. But at z equals 0, you can't take. Yeah. So when z goes to infinity, that means near the horizon. Taking a to infinity does not freeze the x's. But near the boundary, taking a to infinity freezes the x's.
So all the fun is at the boundary, you're saying.
So what I want to say is that these propagators are near the boundary, and these are where the x's are frozen. So for the free string, that's supposed to give me, so doing so this is just a line, a path integral over the 0 modes of x. This is supposed to, and then the thetas, of course, also. That's supposed to give you the Feynman propagator for supreangles.
So can I think of that red line as the path of the string?
Yeah. So that's right. So this is at one value of x and theta. This is another value of x and theta. And then that just tells you these are all points on the boundary, and this should give you the Feynman propagator.
But it's not really a line; it spreads out, right?
Yeah, there's some width of it, but I mean,
in the free theory, it spreads out quite a lot, right? Because all it's doing is enforcing Gauss' law.
okay, but there has to be some boundary between, of course, this and this. But okay, which one? I can make this as fat as I want, as long as, of course, it doesn't. Right. So that's the way I hope to get the propagator, is by doing just this path integral over the 0 modes of dx.
And all of the energy comes from those insertions. So because the string is so floppy, that red line costs no energy. Even though it's at the boundary, even though somehow the red line is energy free, right?
It's at the boundary, but it's not at geodesic.
It's a 0.
Rather, yeah. Yeah, it's the opposite. It's like a 0.
And then so the final thing is these vertices. So the vertices are supposed to come from the B's. So the B field here, it has structure which looks very much so as is something like J1, J3.
So you're saying this is sort of the middle term or the second term of the full action you wrote above? I mean, above you wrote...
That's right. So you get the term, you get this term, and there's also a piece coming from this term, which is something like plus lambda left, gamma AB, lambda right, J, A, so this is the 2, J bar. So it gives you an asymmetric boson also. So of course that's not, in the usual HS5 times S5 action, there's no antisymmetric term for the bosons. So if you go to the large radius limit, then this just becomes something like d theta, t bar theta bar, the x dependence. So this is antisymmetrized in the d and d bar. So and this is supposed to reproduce this term here in the Subrian-Mills cubic. But again, supposed to means I would like it to. But, and this is supposed to, this is going to be like XA, XB. This is supposed to reproduce this term. Now the only, there's an obvious question is why is lambda gamma m, lambda left gamma mn lambda right related to f? I can say something, but again, it's just something.
So lambda left and lambda right, and lambda bar? Or?
Yeah, sorry. I changed notation, yeah, sorry.
But so there are different ghost numbers, these different terms you've written down, or there's also lambda bar term in the first term?
All of this stuff is divided by lambda bar. Everything should have ghost number 0, 0. So why is this related to f? So if you go back to the supernatant vertex.
It's from the S, the full action you wrote up there.
Yes, right.
It said after he decouples the Q exact term, that's the rest equivalence.
No, No, he said in a certain, in the ego state. No, it's not in the ego state.
I think this is just this, yeah, it's,
There's a J2 bar, but I don't see this antisymmetric in J2 term there.
it's in the trace where there is Q of something plus the rest. That's the rest. So probably that's what we get with
Subtracted.
So if you go back to the original superannuated vertex operator, the gluon gets multiplied by dx, so this is the usual Yang-Mills vertex operator. The gluino gets multiplied by d alpha, and the field strength gets multiplied by lambda gamma m double. This is like, in RNS, this is like psi m psi n. So the NMN, the Lorentz current for the pure spinor ghosts, is the analog of the Lorentz current for the psis. And now you can see this is like the dual to x. This is like ddx. This is like ddk. And if you think of this as something like ddx, this is dd lambda bar. So why do I say that? I take lambda gamma mnw and I act with it on lambda gamma mn lambda bar of pq, let's say. This just rotates the lambda, it doesn't touch the lambda bar. So this gives you something, if you take the OP of this, with this is going to give you something like lambda gamma mn gamma pq lambda bar. And now if mn is equal to pq, then this has a term which is proportional to lambda bar, which cancels this denominator. So that's why I want to think of this as being the conjugate to lambda gamma n lambda bar over lambda bar. So that's the kind of argument where I want to see that that's F. But again, it's just hand waving. But it fits together in a way that obviously needs more work. But that's it. Where I am now.
So, yeah, maybe we should first thank Nathan. So at each vertex operator, you mentioned the cyclic prescription. But when you now consider a correlator, how do you ensure that only the planar contractions happen?
So there's something that, so suppose it was a non-planar contraction. So that obviously you could draw on a homogeneous surface. But the point you're making is you have to assure that the holes are always simply connected. Otherwise, it's not going to work. So I think that's your question. How do you ensure that the holes are always simply connected? And I don't know. I mean, as you know, so I should mention, of course, Rajesh and Cormoran studied all of this for the deformed conifold. And there was a similar question, and I guess that was later, Oguri, together with Cormoran and Rajesh, showed how to understand that. And actually, there was another discussion of this kind of ideas by Rastelli and
Gaeto, yeah. Right.
Which was slightly different, but so these ideas, of course, are old ideas.
You think?
I don't know. I don't remember how Oguri showed that there was some.
Yeah, these handles don't contribute and so on. That.
So you would have to find some similar argument, but I have no idea how to.
Could I ask a question that's a bit maybe orthogonal? You know, as you know, and as Rajesh and Matthias and so on have been pointing out, this single trace spectrum of Yang-Mills theory is just sort of letter by letter and then tied together. So it seems to me that a natural question is, and probably it's maybe a simple question, is can you write down a world line action, particle action in area S5 times S5, whose quantization would give you each letter?
Yes. So that's, I mean, Lionel also worked on this. I mean, that's essentially the Strischer description. So that's, so for example, there's a paper I wrote with with Ed, but actually it's much older than that. People, so with Ed, not just with Ed, there's all this group that worked on the twistor string that showed how to compute scattering amplitude. But if you just want to get the spectrum, that was done by Ferber in 1975 or something like that.
So a well-line action whose the answer to which is the singleton.
Yeah. So that's. So I'll write it down just because it's so simple. So you just have a I, Z bar Zi, where the Z's are either these lambdas and mu's of the twistor space, or these, I don't know how to call them psi's. The four psi's of the super twistor. And then the only thing you need to add is that you have a constraint, which is that yi, zi, that's a singlet of the yi, zi.
Okay.
And that gives you the singleton representation.
So then wouldn't it seem sort of natural to just take this action and promote it to a worldsheet?
Yeah. So I have tried, he has tried, he has tried. So obviously there must be a connection between this ADS5 times S5 and these twistor coordinates, but precisely how to do it, I completely agree. So, but it hasn't been found yet. At least.
Is this?
Yeah. Okay.
So if you tried to do ADS3 times S3, would it be totally different? I mean,
Okay, that's a good question. So that is something I just brought up in logic. So in ADS, so everything I did here, generalized for ADS2 times S2 and ADS3 times S3 with Ramon flux. So if you have just Navier-Schwarz flux, then it's slightly different. But there's maybe 0 Navier-Schwarz flux is the same as 1 Navier-Schwarz. I'm not sure. And in that case, yeah, then what Rajesh and Matthias did with ADS3 times S3 should have a story here. But here the story is not in twistor variable, it's something else.
No, I was just going to say, probably even ADS3 times S3, the NSNS deformation, one should be able to write down, right? It's not, it's maybe just not been written so far, but.
So you can do deformation. Sorry, you want to do Ramon flux and Navier-Schwarz?
Yeah. The general case probably can also be written down. It changes. Okay.
So, in the paper with we wrote that.
No, I meant in this formulation, in this cosine type formulation.
Sorry, if you quantize this well-line action, if you look at the states that come from this well-line action, is there some sense in which they live at the boundary?
So again, there's no ADS5 times S5, so I don't know what you mean by boundary. It's just y and z.
Isn't there some transform of this to ADS?
If I knew, so that's the 100.
That would relate explicitly these two.
So
what
that's
you were
where
talking
there is this
I see now.
incidence relation. Twistor space is.
Okay. So you've got.
Well, that's not quite. Well, okay. I can talk about that this afternoon.
Oh, wonderful.
Yeah.
So that's
what's
living where.
Yeah. I'm saying, of course, you can get the spectrum right, but you'd like to get the spectrum from ADS, right? Yeah.
How to connect these y's and z's with these x's and thetas? For me, that's the question.
Just harmonic oscillators will do the spectrum right? Right, because there's this harmonic oscillator. Yeah, it's an oscillator construction. But we want to get it from it, something moving in ADS. What?
As Rajesh and Mike and Matthias, this is clearly the right answer.
This is the right answer, but how is it something moving in ADS?
Can I ask something more pragmatic? So you made this proposal. So what are the checks? What computations can you do now with this proposal?
So that's the embarrassing part. So this was like 2 years ago, and I tried to do some checks, and then I switched gears to try to show RNS is equal to pure spinor. But the problem is that suppose you want to just compute a 3-point amplitude, 3-point half BPS.
Yes.
So because the answer has been known for 30 years, 40 years. And the answer is known in PS624 invariant notation. There's nothing you want to do better than the 3-point amplitude. But to do it in flat space, we know how to do of course, more than 3-point. But the measure factor is not manifest in space-time supersymmetric. This is theta to the 5th. So essentially you integrate over 5 of the thetas instead of all 16. You think of it as coming from, because you have integrations over 11 thetas and 11 lambdas, these somehow cancel each other out. And you can make this completely rigorous. They cancel because of BRST, and it's completely straightforward. But this breaks the PSU24. So obviously choosing 5 of the 16 thetas is going to break the PSU24. So you can get the answer, but you can't get the answer in a nice form. So, I mean, for 10 years I've been trying to get a prescription which gives the usual PSU24 invariant answer. And so I can say it in a different way. This is the bulk to boundary propagator that everybody loves. But you can't write this in superspace. Nobody knows how to write this. The boundary to boundary you can write trivially in superspace. And that was done by Howe and West 40 years ago. Scattering amplitude only needs the boundary to boundary for the 3 point. But if you want to do it this way, you really need to write this thing in superspace.
But is this really, I mean, can you just compute without explicitly keeping all the symmetry and then at the end it works, or?
Yeah, you can, but it's a mess. It's not something. So for example, the whole nice thing about this picture is that we know these propagators in PSU24 invariant notation. And in some sense, it's the only thing you can write down just because. So if you want to grade the symmetry, of course, yeah, I have a powerful student, so I can ask him to do it. I would prefer to do it in a way where you keep the PSU24. I'm sure there's an answer, but. And the answer probably involves twisters in some way. But I don't know how to do it.
So this will be the same as the 3-point supergravity on ADS
Yeah.
amplitude, and you're saying there isn't a nice.
Yeah. There's a beautiful answer which was found 40 years ago. I just don't know how to get it from the string theory.
So, sorry, that is supersymmetric.
It has all the symmetries manifest.
So whose is that?
Howe and West, it's like 1980 or something like that. So they've done the.
This is supergravity on ADS5.
Yep. So it's the whole supergravity multiplet, 3-point, just the 3-point function.
And this involves their chiral superfield.
This harmonic superspace.
Sorry, in which?
It involves these harmonic superfields.
Oh, it's harmonic superfields. Okay. Sorry.
And it's closely related to twisters, so I'm sure it's related to twisters. I can explain it to you.
Yeah, I'd like to. I'm sure we had that reference.
Yeah, I think the point is that for a 3-point function, you can always use supersymmetry to bring the configuration to, let's say, this, to this correlator, the correlator of 3 simple ones, and then you can basically use the supergroup to write it back in the full supersymmetric way.
Yeah, I think we were trying to avoid harmonic superspace.
Oh, you shouldn't avoid it.
I should enjoy it.
Between the stuff that Rajesh and Matthias have done at this proposal, can you see similarities and differences?
Yeah, I mean, so ADS 3 times S3 is the obvious thing to try to understand maybe first. Yeah, so ADS 5 times S5, the difficulty is I think they don't have a worldsheet and we don't have twisters.
The ADS3 cross S3, their fundamental representation of PSU11/2 are the twisters.
They have twisters, but they don't have a worldsheet, I think. Or they don't have
ADS3, no, he's talking about ADS3.
ADS 3 times S3, yeah, they have both.
So that's where one can potentially hope to make a connection. Indeed. But the qualitative features are very similar. This worldsheet stuck at the boundary, the string bits, kind of.
Yeah, but there's qualitative is great, but
What about the other aspects of your construction, like this truncation of the spectrum, the thing that many things were pure gauge?
I mean, this has to do with how you get the trace W strings. And somehow in our case, this has to do with this flux and the fact that only a certain number of modes survive, whereas in your case, you get it by just multiplying together. That I don't quite see. That is very different.
Oh, this would be topological string. So topological string, I think the argument is that it shouldn't matter You know, it should matter just the cyclic order, but not how close these are to each other. It should just matter.
And that's why,
the
yeah.
topology. Whereas in yours, it sounds like you've done a specific gauge fixing of the topology. So that's why you specifically see a mode expansion.
Do you see the spectral flow that they have? Do you see some analog of that?
As I said, my guess is that that's because they've done some gauge fixing. So,
But the physical manifestation of that spectral flow was in this fact that there is this winding around. In some sense, this worldsheet winds around the space-time. There's a kind of a covering.
that I would love to understand. That I still don't understand.
Yeah, the fact that maybe somehow locally near the vertex operators, it's x of z is like z to the w or something like that. Is there a classical configuration? Even just qualitatively, can one see the...
in particular, if you restrict yourself to these vertex operators that really look like ADS3, because you have then... I mean, in ADS3 we know it really comes from this sort of covering and holomorphic covering map.
So in your thing, it was hard for you to write down what this object was, right? Somebody asked you a question. Right? What is the object in the vertex operator which produces the spectral flow? And you said, well, it's complicated, right?
The vertex operator, you know, by its OPEs.
Well, but I think Karesh has been trying to write down vertex operators for it, and you can write it down as exponentials of these free fields. So maybe this can be a bit interpreted like that.
Yeah, but by the way, in the paper, in your paper with Juan, there is one section about doing fermionic duality, preserving PSU1/2. I think that's kind of similar to, because like converse momentum to like something like vortices. So.
It's possible. So yeah, there's some missing. Yeah, I agree.
But can one calculate the OPE of, say, the PSU fields with that and see this sort of, I mean, from our point of view, the spectral flow means that there is a certain OPE with one of the currents. Is there a sense you can calculate, say, the OPE of the J currents with this vertex operator and see that you get a polar border W of some sort?
Yes, I think I can argue that. So at least
that would sort of make more directly contact with the way we describe it, because we characterize our vertex operators by the, as Rajesh was saying, with the OPE in terms of the PSU currents.
I think it should be possible. So again, this is a non-linear model, but you can do the large radius limit in which it simplifies, and I think, yeah, I think that should be possible.
I mean, that would see, but at least that aspect would line up.
Okay, thanks, and we'll reconvene.